Okay, this is the review for Chapter 15, dealing with equilibrium. We've got our 5 multiple choice questions, and then question number 6 is a free response question. So question number 1, we can see we've got 2 carbon monoxide molecules reacting with 1 oxygen molecule to make 2 carbon dioxide molecules. It says delta H is less than 0. Obviously that means it's negative, so therefore it is an exothermic reaction. And the question says, which of the following changes alone would cause a decrease in the value of KEQ for the reaction represented above? So we know that a few things can cause the reactant to shift from one side to the other, but there's really only one thing that actually changes the value of KEQ, and that deals with the enthalpy change. So we know that in this case it is an exothermic reaction. If it's an exothermic reaction, um, um, then we know that heat is a product, so it's as if we take that out, it would be 2 CO2s plus heat because it's releasing heat. So we know that the only thing that affects the value of KEQ is the temperature. The other things can cause reactions to shift to the left or to the right, but by increasing or decreasing the temperature, it does cause the reaction to shift left or right, and it also causes the reaction to change the actual value for KEQ. So a lot of things will cause reactions to shift, but only a temperature change will cause the value of KEQ to change, to increase or decrease. So letter A says if we decrease the temperature, we know that this heat is going to go down when it's as if you've removed some of your product. Because the heat has gone down, it's going to want to replace some of that heat that you've lost. So it's going to produce more heat. The only way it can produce more heat is by causing the reaction to proceed to the right. Okay, and since we know KEQ would be equal to the pressure of CO2 squared over the pressure of CO squared times the pressure of O2. If this reaction proceeds more to the right, it means we're going to be making more product. So this is going to go up. These are both going to go down. And overall, what does that do to our value of KEQ? It makes it increase. So if we chose answer A, that would cause the KEQ value to go up. Okay, here they're saying they want a decrease in the value of KEQ. So we basically need to do the opposite. So if we increase the temperature, again, let's look at what that would be. Still exothermic, so we've still got heat. In this case, if we increase the temperature, it means we're adding more heat, so the temperature's going up. If we add more heat, it's going to want to use up the added product that we've made, causing the reaction to proceed back to the left. So therefore our products would go down, our reactants would go up, both of them. If the numerator goes down and the denominator goes up, then your value goes down. So that would cause KEQ to decrease. So that should be our correct answer. Now, looking at our other choices, though, let's look at how the reaction would shift. It's just a good review of Le Chatelier's principle in general. C, if you decrease the volume of the container, what would that cause the reaction to do? Decreasing the volume is going to cause the pressure to go up. If the pressure goes up, we know that it shifts to the side that produces fewer gas molecules. This side, has 3 gas molecules. This side has 2. So if it shifts to the side with fewer gas molecules, it's going to shift to the right. And now the value of KEQ is not going to go up. However, you are going to get more products and less reactants. So it would cause, this one would cause a shift to the right. D, if you increase the pressure of the container and they don't tell you how they increase the pressure of the container, then you can't assume anything, so we have to say that there is no shift involved there. And then E, if you add a catalyst, all that does is it makes the reaction go faster in both directions. So therefore, again, there is no shift involved there. Okay, and that's it for question number 1. Number 2, for the reaction A plus B in equilibrium with C and D, in order to increase the amount of D, you could A, add more C for D to react with. If I add more C, that means the pressure of C is going to go up. If the pressure of C goes up, it's going to you want to use up that C and cause the reactant to shift to the left. So that's not going to increase the amount of D. That would actually decrease the amount of D. So that can't be that. If we remove some C, so this goes down, it's going to want to make more C, causing the reaction to shift to the right. If the reaction shifts to the right, it's going to increase the amount of D. So therefore, your correct answer would be B. If we decrease the volume or increase the volume, you're going to find no shift at all because we've got 2 gas molecules on this side, 2 gas molecules on this side, so it's not going to shift to the right or to the left with either one of those that you do. And then just like number 1, if you add a catalyst, all that's going to do is make the reaction proceed faster in both directions. Okay, this should be number 3. Number 3 says, given the following reaction, 2A in equilibrium with B and 3C, the enthalpy change is positive, therefore we know it is endothermic. To achieve the maximum amount of products, the reaction should be carried out in what way? Well, if it's endothermic and we want the reaction to proceed to the right, if it's endothermic, we know it's as if heat is a reactant. It's requiring heat for the reaction to occur. So for the reaction to proceed to the right, we want to increase that heat, which is going to make you use that up and proceed to the right. So we would want a high temperature. So that one's out. It says low temperature. That one's out. So it's either got to be C or D because those both have high temperatures in it. Now, would we want a high pressure or would we want a low pressure? If the pressure is high, it's going to shift to the side with fewer gas molecules. So according to this, we've got 4 gas molecules here, 1B2 and 3C, and we've got only 2 on this side. So with high pressure, it's going to shift to the side with fewer gas molecules, so it's going to shift to the left. So we do not want a high pressure, we want a low pressure. The lower the pressure, the more it's going to shift to the side with fewer gas molecules. So our correct response would be D. Okay, then number 4 says, of the following statements, which is or are true? So number 1, the equilibrium constant for an exothermic reaction is always negative. Delta H is always negative for an exothermic reaction, but do we ever have a negative equilibrium constant? No, never. So that is absolutely not true. Equilibrium constants can be very small numbers, but they're never negative numbers. Number 2, increasing the pressure on a system at equilibrium always causes the system to adjust so as to relieve the stress. Generally, yes, unless the number of gas molecules on both sides are the same. If the number of gas molecules are the same on both sides, then it does not cause the system to adjust. So when they use the word always, you always got to be careful with that. So 2 is out. 3, a homogeneous equilibrium is one involving only one substance. Involving only one substance or involving substances of the same type, such as all gases or all aqueous solutions. So it does not necessarily have to only involve one substance. It just has to involve things that are all in the same state. So they all have to be gases or all aqueous. That's what homogeneous means. So 3 is false too. So I sure hope 4 is true. Number 4, the rate at which substances reach equilibrium may be increased by adding a catalyst. Obviously, that is true. You add a catalyst that causes the reactions to go faster. So therefore, is the correct answer. Number 5, at 450 degrees Celsius, the equilibrium constant Kc has a value of 50. So Kc equals 50. Which of the is true of the reaction at equilibrium? So at 450 degrees, has a 50. Okay. So A, the rate of the forward reaction is greater than the rate of the reverse reaction. As we learned the very first day with equilibrium, the definition of equilibrium is that the rates are going at the same speed. The forward reaction and the reverse reaction are going at the same rate. So one of them is not going faster than the other. So A is not true, B cannot be true. C, though, the rate of the forward reaction is equal to the rate of the reverse reaction. That's always true at equilibrium. So I would say that C is our correct answer. And then D, an increase in the volume of the system will cause an increase in the value of C. We know that the only thing that changes the value of KQ is when the temperature changes. So D and E are both out. So it absolutely has to be C. Okay, and then our last one, number 6, says, in an experiment to investigate ozone-depleting compounds, nitric oxide, NO, and ozone are mixed at 200 degrees Celsius, and the following gases equilibrium concentrations were measured. Write the equilibrium expression Kc for the reaction represented above. So we would have Kc, and they specifically say C, so it has to be concentration, even though they're all gases. We want it in terms of concentration. So we have the concentration of NO2 times the concentration of O2, which are products, over the concentration of NO times the concentration of O3. Okay, and then B, calculate the mole fraction of oxygen at equilibrium. Now we don't have the moles, and we don't even have the volume, but we do have the concentrations. And in that case, because all of the volumes are the same, those basically will cancel each other out. So what we're going to do is we're going to put the concentration of O2 on top, so 0.60, over the total concentration. So we've got the concentration of NO, 0.25, plus the concentration of O3, 0.30, plus the concentration of NO2, 0.6, and the concentration of O2, 0.6. So we take those four numbers on the bottom, we add them together, and we get 1.75. We put that under 0.6, so we take 0.60 divided by 1.75, and you get a mole fraction with two significant figures of 0.34. No units, no percent sign, no nothing, just 0.34. Okay, and then C, calculate the value of Kc and interpret what the value of Kc tells you. So we know Kc is right here. So we're just going to put our numbers into the equation. The concentration of NO2 is 0.6. Concentration of O2 is 0.6. The concentration of NO is 0.25. And O3 is 0.30. So 0.60 times 0.60 divided by 0.25 divided by 0.3 equals a value of 4.8. And interpret what this value of Kc tells you. Since the value of Kc is greater than 1, it tells you that you have more products than reactants. That's what the value of KEQ always tells you, is which one you have more of. So that's a reaction that proceeds quite strongly to the right. Okay, then the next one says calculate Kp. We know that Kp is equal to Kc times R times T times the change in the number of gaseous moles. Remember that N is the moles of gaseous product minus the moles of gaseous reactant. So therefore, if we look at our original equation, how many moles of gaseous product do we have? 1 mole here, 1 mole here. So we have 2 moles of gaseous product. Now, same thing over here, 2 moles of gaseous reactant. 2 minus 2 is 0. So this change in N is equal to 0. Anything raised to the 0 power is equal to 1. Therefore, Kp is equal to Kc. So we can say that Kp equals 4.8, the same value as our Kc value. And that's all you have to do on part D. On part E, when the mixture was cooled to a lower temperature, 25% of the oxygen was converted back into O3. Calculate Kc at this lower temperature. Well, let's look at how much oxygen did we actually start with. We had a concentration of 0.60. That means that 25% of that 0.60 molar was converted back. So let's figure out what that is. 0.60 times 0.25 equals 0.15. That means this went down by 0.15, so it became 0.45. Now, everything here is a 1-to-1 ratio from our balanced equation. So if this goes down by 0.15, so does our other product. It's going to go down by 0.15. So NO2, which is also 0.6, goes down to 0.45. So our Kc equation is going to be 0.45 times 0.45. And then if our products go down by 0.45 or 0.15, then we know that our reactants have to go up by that same amount. So NO3 was 0.25, so that's going to go up to 0.4, so 0.40. And our O3, our other reactant, O3, was 0.3, and it's going up by 0.15 as well. So 0.3 plus 0.15 equals 0.45. So we're going to have 0.45 times 0.45 divided by 0.4 divided by 0.45. I guess two of those 0.45s canceled. And we get a value of 1.1 for our Kc value. And that would be your final answer. Okay, and then F, a different experiment is conducted in which 0.75 moles of NO is mixed with 0.75 moles of O3 in a 5-liter container at 200 degrees Celsius. Now, how is that temperature-wise compared to our other one? Okay, the other one was also at 200 degrees Celsius, which is important because what that means is it means that our Kc value is the same. Remember, we learned that no matter what you start with, the value for the equilibrium constant is the same when you're still at the same temperature. So if we have 0.75 moles of NO in a 5-liter container, 0.75 divided by 5 gives us a concentration of 0.15 molar NO. And then the same thing for O3, 0.15 molar O3. And what they want to know is they want to know what's the equilibrium concentration of oxygen at this temperature. The key, again, to understanding this question is that knowing that the value of Kc is the same no matter what you start with. So what we can do is we can say 4.8 equals 0.15 times 0.15. And both of these are unknown, but they have to be the same amount. So we can say x here, and we can say x here. So basically that's going to be x squared on the bottom. X squared, we're going to move over to this side, so it's going to be 4.8x squared is going to equal 0.15 times 0.15. So basically 0.15 squared equals 0.0225. Divide that by 4.8. We get 0.0046875, and then to get x, we have to take the square root of x of that value. So the square root of that, I get an x value equal to 0.0685 molar. And that would be the concentration of O2 at equilibrium. It would also be the concentration not just of O2, it would also be the concentration of NO2. So both of those together would give you a value of 0.0685 all total. And then the last one, G, it says in a final experiment, you've got 0.5 moles of NO, 0.45 moles of O3, blah, 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 are added to a reaction vessel. In which direction must the reaction proceed to reach equilibrium? Anytime they ask about which direction a reaction's got to proceed, you know that you're going to be dealing with Q. So in this case, they don't tell us the volume, so we have to assume that all the volumes are going to cancel out. Q, as we know, it's the same thing as KEQ, just using the initial value. So we're going to use this same equation, NO2 times O2 on the top. So NO2, so 0.25 times O2, 0.65 on the top, and we're going to divide that by NO and O3. So NO, it says, is 0.50 and O3 is 0.45. So 0.25 times 0.65 divided by 0.5 divided by 0.45 gives us a Q value of 0.722. Now in this case, they do not give us a new temperature, but in both cases it doesn't matter if it's this one or this one. The Q value is less than the KEQ value, which means Q has got to go up to reach KEQ. For a Q value to go up, for an answer in a fraction to go up, these numbers have to get bigger and these numbers have to get smaller. These are our products. These are our reactants. So if the products have to go up and the reactants have to go down, in which direction must the reaction proceed to reach equilibrium? It must proceed to the right. By proceeding to the right, it's making more products, it's reducing our reactants, so therefore it has to proceed to the right. And that is it for the review for Chapter 15.